Thanks, Charlie. Good morning, everyone. As Charlie said, I'm Bethany Frew from NREL. So this session is on market design. We've been talking a lot about some very technical items over the last couple of days. So we're pivoting to really the interface between a lot of those physics-based concepts and economics, and how markets can signal for the set of grid services that we need to support reliability, both on a planning and operational timescale. So we're going to have 4 speakers in this panel talking about different aspects of markets, including that interface with resource adequacy and reliability. First up is Mark O'Malley, who's a Leverhulme professor of power systems at Imperial College in UK. He's going to be kicking us off with a framework and kind of how to think about grid services, because ultimately that's at the heart of what we're doing. So I'll hand it over to.
Okay, so first of all, I'm Imperial College London. The fact that it's in the UK is totally irrelevant, right? And to Charlie showed slides the other day at the start to say, and he showed all the countries that are here. He did not include Ireland. I am still from Ireland, Charlie. And Imperial College London, that's it. It just happens to be in the UK. Don't anyone say I'm from the UK. That's not good. Okay, so I suppose just to start out, thank you for inviting me, etc., etc., etc. But I think. Oh, the time. Okay. So just one thing about this. So I'm the Leverhulme professor in power systems in Imperial College London, and the Leverhulme Trust, who I've shown there, they have funded me at Imperial. They've been extremely generous, and the name of the project that they funded me to do there, that the sort of endowed chair I have, is System Services for 100% Power Systems. So it's a big project. There's about 11 people involved over 5 years. We've only really started, although I've been there for a year. It's taken a year to hire a team. So we're just at the start of this. So in many ways, what I'll do is I'll show you a big picture, what we're going to try and do roughly, and then I'll show you some very specific work that we've done. So the work has only started. It's only starting to come out. I thought it'd be useful to go back in time before we, to sort of look to the past and see some learnings we can get from that. So the first, and to, I think it was Mark Alstrom, was it? Or I can't remember who said it, but I mean, these ESIG meetings are probably the best meetings for any academic to come to, because you see what some of the real problems are. And the very first ESIG meeting, and it was UWIG at the time that I came to, was in Oklahoma, Charlie, in 2006, of which I got delayed, isn't it, in Chicago for 2 days, wasn't it? Yeah. So anyway, I just went back to the very first ESIG meeting, or UWIG meeting as it was then, that I was at, and I just pulled some of the slides from it. I think are pretty instructive. And in fact, if you see, I mean, I don't know if you can read there, I gave 2 presentations, and one was on wind in electricity markets. So it's a market session. So you could say nothing has changed, couldn't you? And in fact, the date is exactly 18 years ago, or no, 17 years ago. Oh, sorry, no, the talk I gave on reserve is 17 years ago, exactly. But the point about I'm trying to make here is that at the time when UWIG or ESIG or whatever was starting off, we were sort of up against sort of very low penetrations of renewables, and there was lots of questions to be asked, et cetera, et cetera, et cetera. And I've just pulled out some of the slides there. I'm not going to go into the slides in any detail, but we were, there's an outline methodology there about how to calculate reserves, and there's some results there, et cetera. I have no intention of going into these at all. But I think the point is that at the time, down at the bottom right, I've got a sort of a where we were and where we wanted to go. In other words, at the time, to some extent, the results were local, specific, piecemeal, opaque, and potentially expensive and unreliable. But what you want from results for research is you want them to be global, you want them to be general, you want to be holistic, you want to be transparent, and ultimately then cheap and reliable. And I'm just trying to make the point that nothing has really changed, that, despite we're 17 years on, those principles still apply. Which is sort of just to go back to the past. So now I have to go back to the future. That picture is approximately 1 hour old, isn't that right? Hands up, who was in that picture? We're missing one. Where's Patrick? Oh, there you go. We're talking as the others were coming in, and we're talking about system services, weren't we, Patrick? And we sort of came to the conclusion that system services are probably a little bit piecemeal, a little bit ad hoc, and we're not quite, from a methodology point of view, to go back to the previous slide, there's no real rigorous methodology when it comes to system services. Like, you don't go and someone says, I want new system services. You don't have a methodology. You know, it's not a tech, for example, you don't find in any of the power system textbooks. There's no, so it hasn't become industrialized, processed, or whatever, and methodologies done in it. So that's the sort of the context. I am on topic, Charlie. Just to go back a bit as well to the GPST that I think a lot of you know about. So the GPST is six system operators in the world plus some researchers, and this is the research agenda from it, which I think was mentioned yesterday. And I've just highlighted services in it. So there's 59 research questions. One of the whole baskets of sort of research questions is services. And services is, you know, inverter design has, you know, capability and service and IBR. So it's a very topical issue, and that's when we applied for the Leverhulme Foundation for this grant that I had out of Imperial at. It was the sort of GPST inspired. This is a slide that I use quite often. You know, I suppose at the very top is balance. I mean, the fundamental objective of a power system is to balance supply and demand at minimum costs and acceptable reliability. Unfortunately, my picture covers over the reliability part. But that's fundamentally what this is all about, and it hasn't changed. It won't change, I don't think. That's fundamentally what we do. Balance supply demand at minimum cost at some level of reliability. You can add on attributes to that if you wish, you know, sustainability and all that sort of stuff. And I suppose what's happened in the past number of years to sort of go from when we were in Oklahoma 17 years ago. In fact, when we were in Oklahoma 17 years ago, it was only really about wind. Is there a laser pointer in this? Is there? Sorry. Is there a laser pointer? I just obviously went through lots of slides. There is a laser pointer. Ah, yeah, okay. It was mainly about wind, and then it was about wind and solar. And now really it's not so much about wind and solar, but it's actually about the technology, the power electronics now that sort of interfaces. I mean, I think we've, largely speaking, I think we've really taken care of the wind and solar characteristics as a resource. It's variable, somewhat difficult to predict. I think that work is pretty much done, except for probably on the longer timescales when you need, you know, seasonal storage, etc. So it's really sort of the power electronics piece in the middle between the resource and the power system that really has become the focus. I mean, how many sessions on IBR were there yesterday? So it's all about the inverter-based resources. So if you look at it, then you have this sort of balanced trade-off again, and the trade-off is in the title, you know, balance supply, demand, balance some level of reliability. So you've got this sort of process that goes on, which is minimization of cost, but then you got to say, so it's a sort of an iteration between reliability and economics. But again, if you put in the middle the sort of the slide I had, or the text I had earlier, you know, you don't, where we are now, I think where we are now in this inverter-based resources is, I think where we are is we're been a bit local, because I mean, if you look at the presentations that were going on yesterday, they were very specific and localized about the UK or this, that, and the other, and some system, etc. So you're local specific, a bit piecemeal. At least that's what myself and Patrick agreed to. So sorry, Patrick, to put you on the spot. Opaque and potentially expensive and unreliable. What you want is you want a situation whereby when you have inverter-based resources, that you have some global answers, generic, holistic, transparent, and then potentially low cost and heavily reliable. The guy with the in the top right-hand corner is that I think that there is some level of belt and braces going on with the system operators. You know, I'll tell you what I mean is that sometimes you ask a system operator why they introduce a new service, and they just sort of said, "Oh, well, I think I need it." So I'm being a bit sort of, you know, extreme what I'm saying, but if so, there is a potential that we'll over provide services because we're being ultra conservative, but that's expensive. And of course, if you under provide them, you might black out. So one of the things that GPST did a few years ago is that we produced this report on the left-hand side, system needs and services for systems with high IBR penetrations. And I think that was a very successful document. I think a lot of system operators liked it. It wasn't very, it didn't have a huge amount of analysis in it, because I think we're at the, if you look at some of the work that's been done here yesterday, again, there is analysis been done, but there, if you take what is Deepak in the audience? Deepak is here somewhere, is he? Where is he? Oh, Deepak. Yeah. So, if you look at some of the work that Deepak showed you yesterday, he had a test system and he did some various, so again, I'm not being critical, but I am being critical. But it's that we're still at this stage of sort of trying to understand, on a test system and, smaller systems, we're trying to get some understanding and insights and things like that, etc. We haven't really scaled it up. The reason I put in the pictures of Sebastian, and I think that's, sorry, Andrew, is it? Will, sorry, Will, yeah, sorry, yeah, Will, sorry, yeah. Is that again, and I'm just picked these out at random to some extent, and if you look at the talk that Will gave yesterday, you used the word piecemeal, didn't you? Yeah, yeah. Now, yeah, so I'm just trying to sort of say that there's sort of evidence here that that I'm correct. That's all. You're a witness for the prosecution. In the top right-hand corner, in that diagram there, and you can argue with this. I mean, for example, if you ask somebody, list off the fundamental service or power system, I mean, you'll get different answers. Now, they'll have a lot of similarity, but they will be different. And in fact, if you go to some systems, you'll have a situation whereby if you were uneducated in this area and came in and you listened to sort of Patrick from MISO and maybe Julian Leslie from National Grid ESO, they both run power systems, etc. But if you'd ask them about their system services, you'd get a lot of terminology be saying, a lot of similarities, but they would be different. Yeah, and it's not that they are different, it's just that they've approached it in a different way. Their systems the actual physical systems themselves may lead to the situation where some of them are different for very good technical reasons, but most of them should be the same. So you can argue with the terminology, etc. And then just sort of more evidence or whatever. This is a cut off a website, and if you look at it, on the 9th of October 2023, about 2 weeks ago, AEMO in Australia had launched two new services, 1 second reserve up and down, and they just launched it 2 weeks ago. So there's a situation where people are introducing new services, and of course the reason they did on the left hand side is because inertia in the system is dropping, they're finding the frequency is moving more, etc. But also, Julian's picture's in there because Julian yesterday mentioned that National Grid ESO introduced some new frequency control services, etc. And again, not to sort of highlight things, but I know that when I was talking to Julian, they removed some services when they introduced the new ones. In Australia, they didn't. So you get this situation where people put in new services, but don't remove old ones. You have to ask yourself why. So to that end, so here, I'll do a poll. So does everyone, I mean, this is just a bit sort of simplistic, but does everyone agree that to some extent services is a bit piecemeal, ad hoc? Is that anyone disagree? No one disagree? Does everyone believe that if they were a little bit more, let's say, rigorous methodology, a little bit more structured, that it would be easier to do? There you go, convinced. Now, but how do you do it? That's the question. So in order to start that off, what we did at Imperial was we decided to just be very simplistic about this, not do any, not rush into any simulations or, analysis or whatever. We decided just to sort of look at them and say, is there any way you could just structure the whole thing that has some sort of generic, let's say, basis to it that applies to every system in some way, okay? And if you just take at the very top layer, the primary layer, I mean, the fundamental goal is still that balance, supply-demand balance. That's what you want to do. And in order to do that, the next layer really is where these services come in. They are the things you need to achieve the goal. Does that make sense? Now, there's this old paradigm that goes as follows. What's a need and what's a service? Some people talk about needs and services. I need this, and what provides this as a service. So there's a bit of sort of taxonomy going on here that there's a bit of confusion between things. But nonetheless, we'll call this the services and needs layer. And I'm not intending to go through all those things there, but if you look at them, you have to turn your head by 90 degrees to read them. But if you go through them, you'll see pretty much all the usual things that you'd expect to see. You'd see, I have to do it myself, containment of rock-off, voltage containment, power quality, etc., protection, restoration, capacity, energy, resilience, etc. So they're the sort of things that you would call to be services. And then the next layer down that we sort of decided was the next most important layer is the control layer. you have to enable all this in some way. There's some sort of control actions to be done. And I think a very important sort of point of this is that within that, we've got inertia. So inertia is not, inertia is not a service. Inertia, some people think it is a service. It's not. It's just there. It's nice to have, but it's not actually a service in its own right. I need to go on because I'm 26. I'm nearly there. And then below that's the technology layer. So you've got a situation, they are all the bits and pieces of the physical devices that provide these things. And I suppose what we're trying to do is to try to say that if we could get a sort of global recognition on some sort of generic way of doing this, then you have some sort of framework on which everyone can sort of work off commonly. And just as an example, if you look at containment of rock off, which is there, to provide it, there are 3 things in the control layer that can do it. And then if you take one of those 3 things, there's some of the technologies it needs. So it's a sort of a trickle down type of diagram, which I think could be useful. I'm out of time now, but if you bring it all together, so I suppose what we're trying to do is, well, it's in the context of a bigger picture. So there's the services in there, but if you think about it, it's the system services at the center of the power system that drive everything else. So if you go out here, the vendors are out here saying, what will I build? What technology? I mean, Achilles was here yesterday talking about the wind turbines and what he do. And what he's looking for, he was talking about grid codes, and the difference between grid codes and services is not huge because grid code essentially that you have to do it. So you can see that the vendors are out there and essentially they've been driven by the system services. And there's also some interactions with policymakers. I mean, if the policymaker decides the reliability standards should be greater or higher, it changes things. So it's a bigger context. So finally, then I got to Deepak's picture in here. So Deepak is running the framework needs much more work. It's just sort of the basis, the start of it. There's more we've done, but I won't show it. And this diagram sort of highlights it, is that you've got a situation, if you take cost and reliability, the green area is acceptable. The top right left is infeasible and the bottom right is poor design. You want to be in that green area, but as we keep putting more and more wind or more and more IBR in the system, we've been pushed around that green area. It's higher cost, the reliability, etc. So you need to sort of have some analysis and studies that Deepak is doing to sort of determine where you are in that green area. And as you drift towards one of those boundaries, you can't drift towards the infeasible boundary, it's impossible to get there. But if you drift towards the poor design one, you have a situation where poor reliability and extra cost. So that's it. My conclusions are very simple. And I think the first significant detail level of system work, needs to be, before we do this, there's an awful lot of answers that need to be got from some fundamental sort of systems work. But then if you manage needs and services due to IBR, replacing SMRs, so a rigorous process and methodology, I think you all agree. The ESIC task force is important to mention. Do you need a framework to do this? I think you do. You need some sort of instruction. We've made a start, more to be done. Thank you very much.
Great, thanks, Mark. We're going to move on to Sasha Kuzura, who's in the Brattle group. He's a research associate. And so the rest of these speakers are really going to be leveraging this framework and kind of this concept of system services and system needs that Mark just described. But we're going to dig more into the details of the complexity and uncertainty in the system and how market design can support that or can help to represent some of that complexity, and how we can make adjustments to the market design to be able to represent those factors in operations. So Sasha is going to be focusing on the day-ahead real-time uncertainty in market simulations.
Thank you, Bethany. So from Mark's presentation, we just learned about some services that ensure system reliability. And we're going to zoom out a little bit and see some of the economic impacts of these services. Operational uncertainty can cost you millions of dollars in costs. And so, for example, as we're approaching 100% renewables, the chart here on the right top is a CAISO record for renewable generation from last year. It's fallen many times over since then. But when 98% of your generation is renewable, you need a hedge against your wind shutting out or your solar going offline. So you keep expensive firm capacity online to provide a backup. Similarly, transmission outages and congestion, you need some expensive redispatch to get around those. And in some cases, heat waves can increase air conditioning demand supply, and you're, again, risking system frequency stability there and you may need some expensive generation to kind of provide a backup. So to counter these sources of uncertainty, you have system flexibility, which is the ability of the system to adjust its supply or demand up or down to maintain balance. And a couple of examples of that is that storage can provide reliability. Markets, they coordinate different entities' flexibility resources, and transmission enables markets. And we're going to go through these examples in the following slides. And what I'd like to leave you all with today is that including uncertainty in your planning modeling can help you to procure enough flexibility resources by showing the value of this flexibility. So to illustrate, I have kind of a forest of bar charts here. And there's three groups. The first group is showing is looking at storage. The middle bar chart is looking at markets, and the right group is looking at transmission. And in each case, there's two sections to the bars, right? The bottom section is the value that you find when you're simulating these resources with perfect foresight, no uncertainty. And then the top hashed areas are the additional value you can find by including uncertainty in your simulations. And so for storage, if you're dispatching your storage unit into the day-ahead market, you get some baseline of value, which we measure as revenues. And then if you allow your storage to redispatch into the real-time market in your simulation, then you find additional value because day-ahead real-time uncertainty manifests as price signals. Storage will redispatch in the real-time time frame to exploit those price signals and thereby provide flexibility services to the grid. And you can find, you can more than double the amount of storage value that you find by modeling the uncertainty. So in the middle here, we're looking at the benefits of participating in a real-time energy market as opposed to a bilateral only market. And you could see that when your simulation includes day-ahead real-time forecast uncertainty, you get as much as 30% more benefits from this market formation. And on the right-hand side, we have a similar story. This is with expanding transmission in a system with varying penetrations of wind energy. And your benefits of this transmission can increase twofold or even 20-fold, depending on how much wind you have on the system. So this is all to say that including uncertainty in your modeling can really expand the view of flexibility value that you get from your study. So now we're going to just talk about these examples one by one and go a little bit deeper. So flexibility resources like storage, they're used to balance the system. And what that means in the modeling world is that they're just maintaining supply and demand balance. So in this chart, we have four sort of series, right? The top gray line is your load. The second line is representing thermal unit dispatch. The third line in green is representing your wind generation. And the fourth line is your storage activity. And when we're positioning the system to run in real time, we rely on forecasting. And so in each of these kind of four lines, there's actually two series, right? There's a lighter line, which represents the day-ahead view of your system based on a forecast. And then there's a darker line, which represents actual outcomes seen in real time. And the difference between these two lines, that's the forecast error that you need to deal with. And so to talk through how storage flexibility or other flexible resources can help you to maintain frequency balance, I've put a vertical dashed line on this chart to just kind of walk through the example. So in the day ahead, we're making a forecast, and we have the kind of lighter lines. And on the top, in the load series, you can see that the lighter line is below the darker line of actual load that's realized in real time. So that means we're under forecasting load. And then in the third line, in the green wind section, you could see that the darker line of actual real-time wind generation is below what you're anticipating in the day-ahead time frame. So you've over-forecasted your wind generation. And so in this system, in this situation, you're facing a supply shortage. So what do? Well, one option is to adjust your thermal resource dispatch to kind of flex up. You might need to call on an expensive peaking unit to step in and provide some additional juice to the system. And another option is that if you charged your storage resource from renewable energy, you can just discharge that and displace some of the need for flexing up your expensive thermal resources. So in this way, you could save a lot of money from avoiding peaking usage by relying on low-cost flexibility resources. Now, markets, they provide coordination. They're like the air traffic controllers for multiple entities. And there's a few levels on which markets can provide flexibility. So in the day-ahead time frame, you're kind of positioning the system to manage uncertainty. So you're doing the forecasting, you're doing unit commitment for your footprint, and you're procuring the types of services that Mark just talked about. So spinning regulation, things like that. And then in the real time, now that you've positioned your system to deal with uncertainty that manifests, now the market will kind of redispatch and shift the resource distribution to meet the actual realized demand. So right now we're kind of in an interesting time because several non-RTO regions are looking at market integration. And this is big news because we haven't seen new markets being formed in decades. And these types of questions about how do I form my market, what happens if I participate, should I participate, what kind of market should I participate in? These questions, they rely on modeling to kind of get a sense of what's going to happen in the future. And so when you're dealing with hundreds of millions of dollars in potential market benefits from integration, you want to be simulating forecast uncertainty, operational uncertainty in the day-ahead real-time time frame and beyond, so that you can really maximize your view on the potential benefit you can get. And next, transmission enables markets, right? You can't be trading if you're not connected to your neighbors. And the way that transmission specifically helps with flexibility is by connecting different diverse regions with different diverse resources. So in this really neat NREL map below of the continental US, it's showing different generation resources and loads by areas, right? So the yellow regions are areas with high solar potential. The blue regions are areas with high wind. Green is solar and wind. And then the red dots are your load centers. And if we're doing some blue sky dreaming here, looking at connecting the eastern and western interconnects, then you can start to exploit such diversity, like when the New York City is ramping up for the evening, you have sun shining and relatively lower load out on the West Coast. So you can kind of trade these resources around and balance out some of the lumpiness, some of the uncertainty that can arise on your system. And here's on the right side is a kind of a fun map of Chile, right? And Chile is a vertical line basically, and you have a lot of solar in the desert in the north, and you have a lot of flexible hydro resources in the south. And so in this case, you would use transmission to connect the solar with the hydro resources and basically provide balancing. Because when all your solar is on the same longitude, it might all, it's going to be coordinated in its generation. So it could all cut out at once. So next, I'll give an example of how planning for uncertainty can save millions of dollars in operating costs. So in this system, we're looking at a small system that is looking to expand their renewable generation, and they're striving for 80% in this case. And so these two graphs, they're showing hourly dispatch for a day with high renewable generation. And in the left side, we have no storage. So it's just today's system. We put a bunch of wind and solar into the simulation and see what happens. And then on the right, we have storage in the graph. And each of the layers in the visuals, they're representing generation from a different resource type. So the black line is your gross load. The kind of peachy, peach-colored section is energy efficiency. The brown is behind the meter solar. And so those kind of modify the net demand that the utility sees. And for as much of the remaining net demand as possible, you're going to be generating wind energy because it's cheap, it's free. But because wind energy can fluctuate minute to minute, the output goes up and down, you need to keep a thermal resource online to provide balancing services. And having this thermal resource online actually can displace some of the utility scale solar and wind on your system, because otherwise you risk overgeneration. And so if we put on a storage resource into the system now, 30 megawatts, this storage resource can provide reliability services. And so you no longer need to run your thermal asset as much, and you're able to integrate more of your renewable energy, right? So in the simulation on the left-hand side without storage, curtailment costs accounted for about a quarter of production costs, and these are millions of dollars. Whereas on the right side with storage, your curtailment costs fall by a factor of 4, your annual production costs fall by a factor of 2, and the tens of millions of dollars that you're saving per year in operations, they more than cover the annual payments on your storage system. So this is an example of the cost savings of preparing to deal with operational uncertainty. And this is a small system, so one can only imagine what the impact is on a bigger system. And there's many forms of uncertainty beyond the day-ahead real-time timeframe, and Selin is going to get into that in terms of resource adequacy planning. But you need to be prepared for all of it, right? It's not just looking at operations and whether I dispatch storage. It's that, how is my demand changing year over year? We saw an example recently where rate structures were over-incentivizing behind-the-meter solar, and so customers all of a sudden had more money in their pockets, and they decided to put in a second air conditioner in their home. And that increased system demand by quite a lot year over year. It's an unexpected situation. Sometimes you might have a crypto mining operation that comes into town. You need to upgrade your transmission and distribution system, maybe procure additional generation, and then the crypto mining vanishes. This happened a few times in the last few years. And then, similarly, supply can also change. I mean, there's extreme weather and droughts, which can upend some of your resource planning. There's fuel pipelines freezing over. There's supply chain issues delaying delivery of renewable resources. Geopolitical factors impacting how much fuel you can get. So all of these things are uncertainties, and they can become expensive if you need to get emergency measures to address them. And so system planning should account for these types of uncertainties. And we at Brattle, we can help you look at that if you need some help. These things are going to be on the slides later on, so you can look back. This is me. You can scan this QR code to connect with me and send me an email. And that's about it for me. So thank you for your attention.
Great, thank you, Sasha. So we're going to move on to Selin Yanikara, who is with Polaris Systems Optimization and the Newton Energy Group. So she is going to be focusing more on the interface of markets and resource adequacy and some of the more granular modeling methods that can be used to capture uncertainty and complexity that can impact resource adequacy and reliability.
Thank you, Bethany, and thank you, Sasha, for the segue to my presentation. Good morning. I've been an attendee in ESIG many times, but it's my first time up here, so hopefully we have exciting stuff for you. I will talk about resource adequacy today. So how is it usually done? It's a planning tool, mostly excluding the physical and operational details in the system, but transmission changes the story a whole lot. System-wide metrics that are not quite applicable when we have transmission congestion in the system. And same for operational details, excluding those make valuing flexibility very difficult. Conversely, assessing the true limitation in the system due to operational constraints. So we think we need a new approach. First of all, it's not just long-term planning. All decisions and all timeframes have reliability impacts, including short-term. So do I have enough for the next few days in the face of an extreme storm coming? And we need physically sound power system models as well as operational details. So including transmission as part of the decision process is not an afterthought. So connecting the gap between investment decisions and transmission. Same for operational details. Distinguishing between flexible resources in the system versus inflexible resources. So what flexibility do we have in the system to address surprising contingencies, including outages and weather? and also market signals to provide to all types of participants, generation and transmission. So this chart shows decisions from build and retire decisions down to real-time dispatch decisions. And all these decisions do have reliability impacts, it's just they're different. So if we're looking at week ahead scheduling, we're looking at assessment of the adequacy of the fleet itself. But if we go down to day ahead and intraday decisions, then we're looking at the impacts of all those non-recourse decisions, the inflexible decisions that we make in the day ahead time frame. So dispatch of those and deployment of demand response and so on. If we go down to real time, then we might be looking at the impact of the reserve procurement policy on reliability. So following up on that, some use cases. Again, all decisions have reliability impacts. If you look at an annual system planning timeframe, the question there is, do we have sufficient capacity available for day-ahead commitment? So we can think of multiple historical weather years, all processed in parallel, as well as the time periods in the year. It can be partitioned into weekly periods, bi-weekly periods, or monthly periods, depending on the length of the decisions in the system. And from this analysis, getting the risk locations and periods in the system and generator performance. Another annual use case is this time bringing the real-time decisions, looking at the reserve procurement policy. Do we have sufficient reserves in the system to respond to surprising contingencies, or are we able to replenish reserves in time? So same idea, processed in parallel using cloud computing. Looking at short-term planning for the next 5 days, right? The question there is, do we have enough reserves to respond to contingencies? Sorry, I think I repeated myself. But this is actually a project under development funded by EPRI. This is you can think of it as a continuous assessment. So every day making decisions with some baseline forecast and then looking at the multiple weather contingencies coming up and repeating this analysis daily. One important message is, before we move on to some illustration of these concepts, shortage is local. Looking at this very simple 3-bus model with load and generation in every bus, system-wide capacity is sufficient, but due to limited transmission capacity between bus B and bus C, we have a load shed in location B. So if we assume the value of lost load is $10,000 per megawatt hours, that event sets the price in that location only to vol and not in other locations. Another important operational detail is the impact of outages. Not all outages are known in advance, right? If we look at this 3-day rolling horizon day-ahead commitment structure with some look ahead 1 or 2 days, when we make commitment decisions for Tuesday, we know some outages, let's say that started on Monday, but we don't know, and we can't factor in the outages that will start later on Tuesday. So the question is, what flexibility do we have in the system to respond to those upcoming surprising outages that we don't know of? So what is the reliability impact subject to a base decision plan we already made? So let's go back to what shortage is. Is it just about load shed? But what about events like reserve shortfalls, dispatch of the expensive demand response injectors, and emergency purchases from neighbors? Should those be counted as events? So we provide this flexibility by defining or flagging shortage by detecting it economically. So there are 2 dimensions to this. One is, what is the order of actions taken to mitigate shortage? Do we dispatch the demand response injectors first, or curtail the reserve requirements? So we can control this in our modeling through hierarchy of the penalty of all of those different constraints and in relation to the value of lost load. So what is the penalty of reserve shortfalls in relation to vol? That's going to determine, do we shed load first or reserves? Another dimension to it is what events trigger shortage. So we, again, detect shortage economically. Anytime when the prices anywhere in the system exceed a threshold price, that's going to flag a shortage event. So the relation of the value of lost load to that shortage price threshold is going to determine whether that's an event or not. So we illustrated some of these concepts on an annual study using our standard model of ERCOT, which is based on public data. I just want to note that these results are not benchmarked against ERCOT's resource adequacy studies. We don't have all the operational details that ERCOT has in the model and all the protective schemes that the operators take in the face of events. So this is an annual study for the year 2024. Each week is processed in parallel with 100 generation outage samples per week, so 5,200 samples in total. This is a nodal analysis, so we're going to look at the impact of transmission. We have all the major interfaces in this model and 345 and 138 kV constraints. It's a single year weather study. We're only looking at outage contingencies here. It's using the 2022 historical weather year. So the goal is finding the weeks and locations in the system with capacity needs. And we're looking at the reliability impact of day ahead decisions in this model. So this study took 3 hours to turn around from start to getting the results. But if you look at the total cloud computing time or virtual machine time, it's about 8 to 9 hours. And given the machine we used, I think it translates into $12 or so. So the average relative precision of the shortage probability estimate came to 83% using 100 outage samples per week. So let's start with summary of findings before we go into some detail. Shortage is location specific. We can have local shortages due to transmission, regardless of capacity available elsewhere. Operational policies and flexibility matter. How do we schedule maintenance? How do we schedule reserve requirements and so on? And severity and duration of an event can be different. So this shows for each month that we processed basically the variance of shortage probability estimate for each month. And we can see that December turned out to be a very interesting month. So the question is December indeed the worst month for load shed? But we will see that it's actually maintenance scheduling related local congestion that's causing December to be an interesting month. So the message here is that worst scenario is not necessarily the most interesting scenario. So this shows some general results. On the top left, in the first chart, we see the peak load for each month for each weather zone in ERCOT. If the peak is happening in the morning, that's a triangle. If it's a PM peak, it's a circle. And the bars also show the coincidental ERCOT peak. We see that August actually has a much higher peak than December. But our analysis, previous analysis found that December needs more computational resources or more outage throws to be allocated. On the bottom left, we see average load and generation availability. So how much, it's a measure of how much surplus we have in the system, and that factors in maintenance. Maintenance is fixed in this analysis. It's not moved around in the face of contingencies. And it also includes the forced outages. So we can see that August is a pretty tight month overall. And the bars show the worst hour in that month. And it has an hour where surplus is very, very little. On the top right, we see congestion rent and the resulting transmission violations. So that starts to give us an idea of what's happening in December. Why is it an interesting month? We actually have a lot of transmission violation in December. So it looks like there is some local congestion that we cannot resolve economically by shedding load. At the bottom, we see load shed in weather zones and total shortage. So total shortage hours and locations. Even though we see transmission violations in December, August has much higher shortage, and it also has load shed compared to December. So this is starting to tell us that August has a system-wide problem, whereas December seems like it's a local issue. Here we see the ELCC of different technologies for the summer month for August. On the left, we have the thermal technologies. On the right, we have renewable and storage. A couple of things to note here. And you can see in the background the heat map of shortage, by the way, and the circles are ELCC. So a couple of things to note here. Storage is actually helping a lot. But if you look at the magnified area, we have some wind resources that are not helping at all when we have shortage. And these are actually midday shortages where we have very little wind availability. So the question is, maybe this is a suitable location for more storage. So we can see the locational impacts and locational performance of generation. So let's look at how dispersed is shortage. We saw that August had a much higher load shed, but if you look at this, it's actually concentrated on a couple of hours. And the peak hours in each month are circled in red. So in August, the worst load shed is actually not happening in the peak hour. Whereas December has a very steady shortage, right? We have shortage in each hour, but no load shed. So we'll see what's happening there. So the answer there is actually we have local congestion due to combined impact of fixed maintenance and unplanned outages, and it cannot be economically resolved through area level load shed. So let's talk about another metric, which is how local versus how widespread is shortage. Going back to our simple 3-bus example, where we have shortage in only one location due to the limited transmission capacity. This metric basically measures how local the shortage is. It's the total dispatch in shortage locations or total dispatch exposed to shortage divided by the total system dispatch. So in this example, we only have generator B that is exposed to shortage. If we divide that by total dispatch in the system, the shortage localization index, as we call it, is 0.4, indicating that we have a local issue. If this value is equal to 1, shortage is going to be system-wide, meaning we have all generation exposed to shortage. So if we look at for each month, this shortage localization index, and this is the spread for all the outage throws, we see August has the localization index close to 1, meaning that it has a system-wide issue, whereas December is very close to 0, meaning it has a very local issue in every other month, actually. We can also see that by looking at how much total generation is exposed to shortage. Again, December has shortage in each hour, but only a portion of the generation is exposed to shortage, whereas in August, this number is much higher, but it's concentrated in 1 hour. So let's go back to our general definition of shortage. In these examples, we were only detecting the load shed events and transmission violations as shortage, but what about other events? So we reran August that has a system-wide issue with a lower price threshold, meaning we might catch other events as shortage events. So if you look at load shed, it's exactly the same, but if you look at the total shortage hours and locations, we actually have an increase. So what are those events that we didn't catch before? So those are actually reserve shortfalls and or congestion price. If you look at one particular draw that we didn't catch as a shortage before, it's actually, ERCOT has 2 reserve curves, online and online plus offline. There's a shortfall for online reserves in that hour. So we're now catching this event as shortage that we didn't before when we had a price threshold that was equal to value of lost load. So this is showing the price heat map of 2 different days or 2 different reasons with shortage. On the left, you see August. Again, prices are high in everywhere in the system. We have load shed in multiple places. So we have an availability issue. If you remember the surplus graph of August, it was much tighter than other months. On the right, we see December that we established. We have a local issue, and we can actually see that geographically. If you look at that magnifying glass area, that's where the prices are high. We have a transmission violation actually due to simultaneous maintenance of units at the same location, combined with unplanned outages. So it's more economically resolved by the transmission violation as opposed to area level load shed, because the load locations are actually far to this generation location. We actually reran this by staggering the maintenance at this location of those different units, and that completely resolved the shortage. So the question is, what about weather, right? Outages are not the only contingency. In the face of weather and in the face of multiple generation outages, how do we solve this in a reasonable time? If we think of weather scenarios translated into load, wind, solar, and for each of them looking at multiple generation outages, how do we efficiently evaluate possibly tens of thousands of those scenarios? So we have some computational tricks for that. There's multiple dimensions to it. There's the weather scenarios and time periods aspect, which we handle through stratified sampling. I will talk about that in more detail. In terms of the random outages, we have an integrated scenario reduction. So it's integrated within the optimization. Well, I will talk about that as well. So starting from the random outage dimension, which is integrated as a scenario reduction within the optimization, we start with a base plan. So solving the day ahead unit commitment with known outages at that time, and then using a simplified formulation for day ahead optimization with random outages. So that can be relaxed unit commitment, fixed storage to the previous step, and so on, to be able to quickly filter through critical outage samples. And then for those that we detect as critical, then we solve only those in detail using full unit commitment, storage optimization, and so on. If you think about the weather dimension and the time period dimension, we employ stratified sampling methodology. So if you look at this picture, we have the last weather scenario that we evaluated, multiple outage samples. It's clearly not a critical scenario. So do we really need to evaluate that many outage samples for it and waste computational efforts? So the idea is, let's run some number of statistically significant enough outage samples for each weather scenario and for each week. I didn't put the time dimension here for simplicity, but it's the same idea. And only those that have some shortage, we run more outage samples for those. So it's an efficient allocation of our computational resources. And that allocation is going to depend on how much variance of shortage probability estimate do we get from the first stage. So the idea is, let's evaluate outage samples for those interesting scenarios. So in this example, this last weather scenario that exhibited no shortage in the first stage, we don't bother running any more outage samples for it. So we did this for this ERCOT run. On the left, you see the original results, which is 100 outage throws for each week, so 5,200 samples. The turnaround for that, it was 3 hours. On the left, we performed additional samples for each week, so 2,700 outage throws, additional throws for each week. The turnaround time for that was 11 hours because some weeks took long. But one other thing I wanted to point out there is we have load shed events, if you look at April and December, that we didn't catch with our initial stage. So we see more outage situations that can actually lead to load shed events in those months too, that we were able to only catch when we ran additional outage throws. So to bring it all together, resource adequacy can assess the impacts on a physically detailed nodal model and operationally accurate model. There are many examples of that, like unit commitment, power flow constraints. Assessment should be both for planning and operational studies, answering different types of questions. And operational details should be part of long-term planning as well, because they impact study outcomes a lot. Things like not all outages are known in advance and not all decisions are flexible. So I illustrated today inclusion of the transmission model with unit commitment and storage optimization, but there can be other modeling options. So sharing with neighbors in the face of contingency, impacts from other energy systems, so synergies with the gas system as well, and participation from load. So all of these can be looked at. And that's all from me. Thank you.
Thank you, Selin. We'll move to our next or final speaker, Nikita Singhal from EPRI, who is a senior technical leader. And she's going to be focusing on storage in markets, how markets can integrate storage more efficiently, how computational methods can be used to represent and simulate different scenarios with storage to evaluate those different market design options. So Nikita, over to you.
Thanks, Bethany. Good morning, everyone. Today, I'll be talking about advances in energy storage modeling for improved market efficiency. More than solutions, I think I'll start off with kind of focusing on the challenges that are still outlying and advances that we need to make in order to ensure that we model these resources accurately to take advantage of all the other issues that the other panelists have brought up, like, for instance, storage providing flexibility to address forecast uncertainty, providing ancillary services. But there's a lot of ground that we need to cover in order to kind of model these resources and accurately to improve market efficiency. So I'll start off with kind of introducing the outlying, the outstanding challenges to better integrating these resources into wholesale electricity markets. And then I'll focus in on one of the challenges, which is to do with enhancing computational efficiency. So a solution for that. But we are at EPRI, we are beginning to work on addressing these different challenges and different projects. But just to start off on what these challenges are, kind of divided these challenges into different buckets. There's the day-ahead market, real-time market, ancillary service market, and miscellaneous. Just to start off, now FERC Order 841 was very instrumental in kind of in integrating these resources into electricity markets. It enabled the participation of these resources into energy markets, ancillary service markets, and capacity markets. But what was essentially done was that the way the ISOs responded is by introducing a participation model for these resources to participate. But the beast is always in the details, right? And the two regions where we're right now seeing increased penetration is in California and Texas. And based on what we're seeing, there's a lot of modeling challenges that they're seeing. So they're having to make changes to the market clearing software on the fly. So it's pretty much like you're driving the car and having to kind of address changes and issues with the car while you're driving it. And one is to do with computational advances that are needed to simplify state of charge management. Now, what happened is that FERC Order 841 required that all the ISOs allow for the batteries to self-manage their state of charge. But there were two ISOs that also allowed for the ISO managing the state of charge of these batteries. We have conducted prior studies to show that the ISO managing the state of charge of the batteries might be more efficient, might result in reliability benefits as well as profits for these assets. But the one hurdle when it comes to ISO managing the state of charge of these batteries is the fact that it can be computationally complex. And the complexity comes from modeling the state of charge explicitly, which kind of impacts the solve time. And you may not be able to solve these problems, especially in the day-ahead time frame in time to post the solution. So we've kind of focused in on to simplify ISO, how ISO could manage the state of charge by introducing something called wrapper energy constraints. But I'll be discussing that in the future slides. The second challenge in the day-ahead market comes from how these resources can be used and managed in your reliability unit commitment processes. So these are intraday processes wherein you are actually committing sufficient capacity to take care of your load to make sure that you can reliably meet your forecasted load. In the day-ahead market, you're committing capacity against the offers and the bids that are submitted, but in reliability unit commitment, you're actually using the forecast, right? What's happening today in all the ISOs is the plans, at least in the regions where there is battery, is that whatever happened in the day ahead for the battery, those schedules are kind of fixed in reliability unit commitment. As a result of that, there may be some inefficiencies. Basically, this is the last opportunity for the ISO to commit any long lead units. Any of these thermal units that need an advanced startup notification, the last opportunity to commit them will be in your reliability unit commitment. And if you have any issues from state of charge management, given the forecast that you are modeling in reliability commitment, that you may not see that because you're just fixing the schedules of the batteries, right? So there may be some inconsistencies where you may not commit thermal resources to take care of those inefficiencies that may rise from these batteries, especially as we start to see gigawatt scales of batteries being integrated into the grid. Moving on to the real-time market, there are majority of the ISOs in the US now just looks, especially in the real-time economic dispatch period, it's just looking forward at the next 5 to 10 minutes. And that kind of is very myopic in its view. There are two ISOs, which is CAISO and New York ISO, which looks at the next hour. So they at least look forward to the next 12 intervals. What may happen is that given the real-time market is so myopic in its view, it may discharge these batteries preemptively without knowing that, hey, there's going to be an issue later in the day. So, you might kind of like suboptimally discharge these resources, given that the real-time market doesn't have a view into what's going to happen in the future. So there are issues. Now, this is an issue with just markets that model the next hour. So imagine this issue, how big this could be when you're looking at just the next 5 to 10 minutes, because you may not be prepared for the evening ramps. So there is an issue of kind of coming up with better ways to manage the state of charge of these batteries in the real-time market. What's happening is some of the ISOs have suggested that, the batteries can submit a biddable parameter wherein they can indicate where they want to be at the end of the hour. Now, there could be some gaming concerns with that, but we've suggested some alternate ways where this could be done by using day-ahead information, using a value offer to what the value of storing a particular amount of stored energy is to the asset owner. Now, even if you do have multi-interval real-time economic dispatch problems, there's the issue with not settling on all the intervals. Today, what we do is that we solve for 12 intervals, but we just settle on the binding interval. And the rest of the intervals are just advisory, right? So a storage resource might be kind of dispatched in a way that, to address an uncertainty that's going to happen later in the hour. But as the horizon rolls forward, the uncertainty may never be realized. As a result of which, the offers, the benefit that the battery owner was hoping to make, that may not be realized. It certainly helps the system, but there is kind of like there's an incentive compatibility issue with the way these markets are structured. So we do need to kind of come up with better incentives for this. One solution that was being toyed around in the ISO New England region was to settle on all the intervals, and then as you're moving the horizon forward, you're only settling on the deviations as you're moving the horizons forward. Another idea that we're thinking of here is to kind of come up with some kind of an energy capability product, talking about introducing more products. It's about just essentially holding back enough energy to ensure that you can actually meet the needs of future time periods. That way you get kind of like also a payment for that service that is being provided. So think of it as holding back state of charge to address issues that may happen later in the day. Now, when it comes to ancillary service markets, there was mention of batteries providing ancillary services. And in fact, one of the main incentives for these resources to participate in that market is that they are limited in terms of how much energy they can store, right? Think about regulation, spinning reserve, and like contingency reserves. The amount of sustained response that you need to provide these services, there are something called performance requirements. That's much smaller when compared to energy. In order to provide regulation, you need to be able to ramp up within 5 minutes, but provide a sustained response for about 15 minutes in most of the regions. Whereas for contingency reserves, as per NERC standards, you need to provide a sustained response for at least 60 minutes. Now, what's going to happen is that with most of the ISOs across the US use something called a reserve cascading model, wherein they value regulation reserve more than contingency reserves. The prices for regulation tend to be higher given the way these models are modeled. With batteries in the picture, and given the fact that the sustained response for contingency reserves is longer, it may be the case that the contingency reserve duration requirements may be the binding constraint, right? So you want to kind of pass on the signal to the participants saying that I am seeing a scarcity of contingency reserves. I want I want that to kind of be indicated in the prices. But given that we're using a cascading reserve model, you'll end up seeing prices being higher for regulation still. So that's kind of like need to rethink whether we should rethink the paradigm of whether we should continue cascading reserves in a future where batteries are a dominant kind of player in the resource mix. The other issue comes with making sure that you're considering enough headroom to provide ancillary services. So considering the feasibility of ancillary service provision. This requires the explicit modeling of the impact that ancillary service provision can have on the state of charge constraint. A very unique, and I thought this issue that was very interesting that is being observed in the one region, which is in Kaiso, is in the impact of them kind of changing the state of charge constraint to also include the impact of regulation down and regulation up in addition to charge and discharge energy. So you would see the way they've structured their thinking of including this constraint is that state of charge in a current interval is dependent on what happened in the prior interval with respect to state of charge plus energy decisions now and regulation up and down decisions now. Why regulation is thought to be included in this constraint is because it's the one reserve that's being deployed more often, and that's the service that these resources are hoping to provide because it's valued the most. If you were to structure the constraint this way, the optimization algorithm is quite smart. What happens is that you would think that it would arbitrage between the charge and discharge, but it started to kind of arbitrage between reg down and discharge of energy. So that kind of resulted in reg down being maxed out. You had too much regulation in the downward direction, and it resulted in kind of negative prices, which created a concern amongst the asset owners that, hey, now I need to be paying to provide regulation down. So this is kind of so there are these subtle challenges where you really need to kind of look into the math behind how you model, the beast is always in the details, right? How do you model the ancillary service impact? And now this gets into kind of how often are these ancillary services deployed and how do you model them? And we're going on introducing multiple different ancillary services. So energy adequacy when it comes to ancillary service provision is going to be key, especially with these energy limited resources. The last bucket that I've included here is miscellaneous. So this is kind of like problems that still need to be addressed in this general area. One is about representation of degradation costs, whether this should be captured in just the offers that are submitted by the batteries, but there's also a push of kind of capturing this degradation cost within the market clearing software's problem itself. This is kind of like, might be like traditional generators might argue that they also go through wear and tear, so they would also want to be represented. Their wear and tear costs also would want to, they would request for that also to be represented. So in order to be kind of unbiased with respect to technology, there's a whole debate on should degradation be represented at all in these market clearing software problems. Market power mitigation is another big one. The way that most of the ISOs are suggesting that these batteries be mitigated is by looking at the historical prices in the last few days or weeks, right? And the arbitrage differences are kind of like used to estimate what the opportunity cost would be, and then that's what's used to develop the reference bids. What happened in the summer heat wave in Kaiso is that these reference bids for normal conditions could look extremely different, but and they also had reference levels that were based on normal conditions. But under extreme events, you're going to see price differences that can be in the range of $1,000, for instance. So these resources may be mitigated down and then be discharged preemptively because of the fact that they were mitigated down. I'm talking about batteries. So there is a need to kind of develop better market power mitigation approaches to account for also extreme events and what do opportunity costs look like in those extreme events. Another, I guess, another topic of discussion is what prices would look like in a high renewable mix with a lot of batteries participating. Right? Folks think that because we are basing off our prices today on marginal cost pricing, we expect that, hey, because there's going to be such a significant penetration of renewable resources, the prices may all go down to zero, or it can swing between scarcity pricing. But storage does a very unique thing. The fact that you are coupling different time intervals through the state of charge constraint, you may land up seeing prices that show a scarcity in an interval where there is no scarcity because of the fact that you have storage in the picture. So essentially think of what storage does to temporal pricing is what transmission does to locational marginal pricing, right? So there's a lot of kind of research also needed to look into what the prices may look like in this future. Now I'm going to kind of dig deep into one of these topics. We are kind of we have a lot of research going on many of these challenges that I just introduced to you, but let's focus in on the computational advances to simplify state of charge management, because this is a big one, right? If you were to if the ISOs were to choose managing the state of charge of these resources, it results in better economic efficient solutions, reliability and profit to the generator. But the one hurdle was with computational tractability, right? So we looked deeper into how could we address that. And we have this report published, which is available if you were to scan this QR code. This work was done in collaboration with my colleagues at EPRI, Walid Aslam and Adequacy, as well as Russ Philbrick from Polaris System Optimization. So we've tested out these approaches within the simulation tool being Power System Optimizer, the PSO. And the whole idea and the motivation behind this work was to ensure that we could manage the state of charge of these resources from the ISOs and at scale. By scale, I mean, we ran simulations with, let's say, thousands of batteries in the picture with different configurations. This could vary in terms of megawatts and duration specifications of these batteries. So what I'm going to do is introduce you to the traditional formulation. What is the traditional formulation going? How does it look when you explicitly track the state of charge in the operational time frame? And then also introduce an alternate formulation that we refer to as the rapid energy constraint formulations, and then compare the two formulations in terms of course, computational efficiency, because that was the whole idea behind the study. And then if we were to switch to this kind of a rapid energy constraint formulation, how does it impact economic efficiency, reliability, the state of charge profile of the batteries, and as well as price formation impacts. And the one key thing that the participants would want to know is how does it impact the revenues of their resources, and a few kind of future directions that we've thought about. So digging deep into the traditional formulations and committing the cardinal sin of kind of introducing equations here, because I realized that I haven't seen any presentations so far in the last 2 days with equations, but bear with me, it's just 6 equations. So the traditional formulation essentially requires, the complexity comes from requiring the chronological hour-to-hour modeling of state of charge trajectory. So you have to kind of model what the state of charge is in every single interval. And what you do in one interval with respect to discharge and charge can have an impact in the future interval, right? So there's this whole temporal coupling aspect that can kind of create a complexity. Second complexity comes from also introducing a target state of charge or a desired state of charge level that would be enforced at the end of the optimization horizon. So these constraints essentially time coupled and hard constraints, which make this problem really hard to solve. We've actually heard feedback from ISO New England wherein they tested managing state of charge of the batteries themselves, and they were kind of limited to just 25 batteries. If they were to have more than 25 batteries, then they cannot kind of continue managing the state of charge of the batteries themselves, because they would not be able to solve the day-ahead problem in time to post the solution, right? And I guess the constraints, digging deep into them, what do the constraints look like? It's essentially, the first constraint is the state of charge in the current interval is nothing but equal to what the state of charge was in the previous interval, minus and also accounting for the charge and discharge activity, while accounting for the round trip efficiency losses of the battery. And the second equation is requiring what the state of charge should be in the last interval of the optimization horizon. And so you can have an input as to what the target state of charge should be, and then the feasibility constraints that the state of charge does not go beyond the bounds, the minimum and maximum state of charge limits. So you see there's this daisy chain of constraints wherein you have to kind of model all the time periods. And this, for instance, for one single battery, let's say if you have 24 intervals in the day ahead, you would have about 48 constraints here, and then 24 different constraint, sign restrictions on the state of charge variable on the minimum side as well. So think of it as 72 constraints. The alternate formulation that we explored is something what we call as the wrapper energy constraint. Now the idea here is that instead of explicitly modeling state of charge, you are kind of enforcing the trajectory of the state of charge and target state of charge implicitly. And this is done through kind of monitoring what the energy exchanged is over a time window. So a time window here is defined as, think of it as a chunk of time. So let's say if you have 24 hours in the day ahead problem, you could have one time window, and that time window is essentially 24-hour long. You could have two time windows, with each of which is 12-hour long as well. And that depends on how you would determine these, what the time window should be, can be based on some heuristics of past data. If you have some forecast into what the prices look like, what does the daily cycling pattern of the battery looks like, you could use that information to set what the time window is. So the idea here is to kind of reduce that explicit modeling and the constraints, number of constraints and variables required from explicit modeling to an implicit modeling. So the first constraint here is essentially to account for the efficiency loss of the battery. So the sum of my discharge decisions and the charge decisions should be equal to what the state of charge was at the beginning of the time window minus what the target state of charge is. So essentially, you're saying that you cannot discharge more than what you charge time, and while accounting for the round trip efficiency loss. So here it says that if you were, let's say you have a beginning state of charge of 50% and a target state of charge of 50%. So then the net exchange over that time window needs to be 0. You can move up, but you need to come back down at the same point. The next two constraints are to do with the duration of the battery. So the amount that I can discharge needs to be within what my state of charge was at the beginning minus what the minimum state of charge is. So let's say you started with a 50% state of charge. Over the next time window, the amount that you can discharge is essentially just that 50%. So this is, and the same on the other side, third constraint is to do with charging. You might think that this is a little conservative because there could be an opportunity to charge back to, right? So yes, this approach is conservative in terms of how often the battery could be utilized, but you do have the flexibility to play around with these parameters on the right-hand side by using dynamic schedules for what the target state of charge should be and the initial state of charge level should be to kind of, and also the length of the time window to kind of control the kind of charging pattern and discharging pattern that you would need. So we tested these two formulations on a New York ISO test system. We had a zonal model of the New York ISO system with 11 different areas. And I'm just going to kind of get into what the battery specs looked like. We had about 1,000 different batteries that were introduced across 6 different areas within these 11 zones. And the megawatt capacity of the batteries ranged from 3 megawatts up to 40 megawatts, and we had a total of about 8 gigawatts. Note that New York has an aggressive target of having about 6 gigawatts of battery in the next few years by 2030 anyway, so we just kind of bumped it up a little bit more. And then the megawatt hour capacity is between the durations that we chose were from between 2 to 10 hours. We conducted these simulations mostly in just the day ahead time frame because that's where the complexity issues are actually. And then we also did co-optimize energy and ancillary services. One thing we did not consider is ancillary service provision from storage because we wanted to kind of just see how kind of focus on just energy provision first before we extend these wrapper constraints to also consider ancillary service provision. We started off with choosing a 12-hour time window because of the way we saw that the batteries were being used in the ISO state of charge management anyway. It was just a single cycle in a day. So the differences here in terms of the problem size, it's the state of charge constraint formulation as expected had a larger number of constraints and variables. You can see that the average number of constraints and variables in the state of charge constraint is much larger when compared to the wrap energy constraints. This essentially resulted in the computational solve time for the state of charge constraints being higher. So on the right side, you have a figure of what the solve time looked like for a year across the different days using these two different formulations. So you can see that in general, the wrapper constraints perform better in terms of computational solve time. And this is key, right? Like, because you need to be able to solve these market clearing problems in time to post the solution. In terms of the average, solve time across the year, average time per horizon there as well, wrapper constraint perform better. You can see that in the left figure. Now, the one other impact that you would want to think about, hey, how did the production costs change with these two constraint formulations? So when we looked at the average cost across the year, so the figure essentially shows you what the cost looked like on each day of the year. The average daily cost, you can see that there was in general, the state of charge constraint performed better. And this is expected because you're explicitly modeling state of charge, and there are some approximations in the wrapper energy constraint. There was an average 0.43% increase in the operating cost with the wrapper constraint formulation, so it didn't perform as well as the state of charge constraint formulation. Also, just for the geeks in the room, the MIP gap was set to 0.1%, so you can kind of relate to what the production cost savings mean in terms of percentage there. If you were to look at the annual cost, the difference between these two approaches was about 24 million. That's significant, right? If you were to think about it over a year, you would have a 24 million difference in production costs with one formulation versus the other, with the state of charge constraint being better. But I'll talk about more as to how we kind of narrowed that gap in the future slides. Now, if you're curious about what is the state of charge trajectory and the LMP impact and the impacts on the prices look like from these two constraints, we've shown figures for one single battery just for illustration purposes, which is a 12.5 megawatt battery with 4-hour duration and a 0.85 charging and discharging efficiency. We started with 50% state of charge, so that's on the figure on the left, with 25 and also ended with 50% state of charge at the end of every day. So you have like 6 kind of dotted lines that represent 6 days in a week. You can see that the wrapper energy constraint formulation, essentially the time window was set to 12 hours. So you can see that it charges, the orange line goes up and then discharges back and comes back to the same point that it started at the end of the time window. Whereas you may land up seeing a more a better behavior with the traditional constraint formulation where the discharging is restricted to the times when the prices were actually high. Now, there is the concern that you will see a little lesser utilization of ESRs of the electric storage resources with the wrapper energy constraint formulation. So given that the traditional approach has a better utilization of storage, you have more storage utilization, that's going to result in flatter prices. So the LMPs as well on the consequently on the right-hand side, you can see that there's a flatter profile for the traditional approach versus not for this can be a concern, right? You're using the storage less with the new formulation that we have proposed. Now, because you're using the storage less, the obvious fact is that it's also going to result in lower resource revenues. In this figure, we've showed you what the annual revenue of the different resources looks like. On the y-axis is the annual revenue, and then the 1,000 different batteries on the x-axis for the entire year. And we've kind of presented the batteries by the different 6 areas that we had placed them in. You can see that in general, the traditional approach is resulting in higher revenues, whereas the wrapper energy constraint approach is resulting in lower revenues. So this is going to be a concern. The production costs also are higher. The revenues of the batteries are potentially going to be lower. The utilization may be lower as well. But then we started to think about what were to happen if we were to play around with these parameters on the equation on the right-hand side. So we modified the time window for just the batteries in one area. We focused in on just the one area where we saw a lot of difference in the revenues with the area D. We changed the time window from 12 hours to 24 hours. So you have 3 different lines shown in this figure. The new one is the green plot, which is the wrapper constraint formulation with the modified time window. You can see that one small change like this resulted in the batteries kind of having a higher revenue in general in area D, even higher than the traditional approach actually. And it also impacted the revenues in other regions. And so basically what we learned is that this new formulation is promising in a way that it does, it can result in better, solutions, but it does require better understanding of the market conditions and forecasts, as well as the risk tolerance of these asset owners. When it comes to costs as well, with this new formulation, you can see the last column, it resulted in the average cost reducing when compared to the original wrapper constraint formulation with 12-hour time window, as well as the solve time was improved. On an annual basis, the difference now was observed to be just 11 million when compared to 24 million earlier. So there is the gap between these two approaches reduced, but it kind of comes down to the heuristics that are used. Just to kind of conclude, this was us exploring how could we better manage the state of charge of these resources in a computationally tractable manner. This was all in the operational time frame in the next day and then the real-time market as well. But where this approach could really be beneficial is in planning problems where you have to look at lots of different scenarios like Selin introduced. And there is an issue that most of the software vendors are complaining about, especially with chronological modeling with these resources, especially batteries, where some of these planning problems are going to be hard to solve, especially with years and years of data. So this constraint, there is kind of the scope to extend them to be used in the planning time frame. We do want to do some additional work with just understanding the influence of these different parameters in terms of, just time window duration, how would it change with dynamic schedules, what role does the resource mix have, and depending on manufacturer warranties as to how many times you want to cycle the resource in a day. So kind of need to develop some future work on just streamlining and automation of these parameter selections so that the resource owners so that the onus is not on the resource owners and the ISO operators to select these parameters, but kind of have some decision support tool to say. We did kind of focus on just energy provision, but we do want to kind of explore there is the use of these wrapper energy constraints with also ancillary services provision from these batteries, and then how would this look like in real time? In real time, it's not so much of a problem with computational tractability unless you do decide to extend the optimization horizon of the real time, which might be one of the solutions to real-time zero charge management issues, and also application of these constraints with hybrid storage resources. So yeah, I did introduce a lot of challenges, but then one solution to this, and we have more work coming to address some of the other challenges as well that I laid out. And with that, that's my presentation. Thank you so much. Looking forward to the discussion.